Hi guys, today we're going to answer the question, how can we solve related rate problems? So let's just look back at a question we've done before, y equals x. And we're going to look at the rate of change of both variables or both sides of the equation compared to x. So for the left-hand side, I can write dy over dx, change in y compared to change in x. On the right-hand side, I'm interested in the change in x compared to the change in x. Well, that's really just going to give me 1. Okay, so let's look down at number 2. Number 2, the radius r and area a of a circle are related by the equation a equals pi r squared. We're going to look at how both variables, or I'm sorry, both sides of the equation are changing compared to time. Let's just think of why we might want to do this. Let's say we have a really, really shallow puddle, so we're not even really concerned with its depth, but we're interested in how its area is changing. So we could look at the relationship between the rate at which the radius is changing and the rate at which the area is changing. So we always start these related rate problems by writing an equation not using calculus relating the variables that we're interested in. Then we look at how both sides are changing compared to time. So for change in area compared to change in time, I'm going to write dA over dt. For the derivative of r squared, I'm going to use the chain rule. I'm going to get 2 pi r times dr over dt. Okay, so now let's just think about something. If I were taking the derivative of x squared with respect to x, I would get 2x times the derivative of x, which is just 1. But now if I were taking the derivative of y squared with respect to x, I would use the chain rule and say 2y times the derivative of y compared to x, times the change in y compared to the change in x. Okay, so that's why the derivative of r squared isn't just 2r. The change in radius compared to the change in time isn't necessarily 1. So I have to write dr over dt. Okay, so for part B, when the radius is 5, the radius is increasing at a rate of 0.5 centimeters per second. So this value here, the 0.5 centimeters per second, that's our dr dt. The fact that this is positive lets us know that the radius is increasing as time goes on. So let's plug in the numbers that we know. We have dA over dt equals 2 times pi times 5 times 0.5. So then we get that dA dt equals 5 pi, and the units for that are square centimeters each second. It's telling us how much the area is changing per second at one instant in time. Okay, now let's flip over. We're going to look on the next page. Oh, wait. Right, okay, perfect. So the length of a rectangle is decreasing at a rate of 2 centimeters per second, and the width is increasing at a rate of 2 centimeters per second. When the length is 12 and the width is 5, find the rate of change of each of these three quantities. Okay, so for all of these problems, the first thing I would do is I would draw out a diagram. So I would draw the rectangle. Anything that's changing has to be written as a variable. We'll talk about why in a minute. So L, the length is changing, so I'm going to label that as L, and in parentheses I'm going to put 12 centimeters, which is the amount that L is at the time we're interested in. The width is also changing, so I have to write it as a variable. At the time we're interested in, the width is 5 centimeters. dL dt, I'm going to write as negative 2 centimeters per second. This is a negative rate of change because the length is decreasing. For dW over dt, I'm going to put positive 2 centimeters per second. We have a positive rate of change. The width is increasing by 2 centimeters each second. Okay, so now I want the rate of change of the area. So I always start these problems the same way. I write an expression for area, not using calculus, but making sure that any quantities that are changing go in as variables. Because think about it, if I just put area equals 12 times 5 or 60, and I said, okay, what's the rate of change of the area? Well, based on this, it would just be 0, right? The rate of change of 60 is 0. But that's not the case here. So we don't want to use that. Now let's look at how both sides are changing compared to time. So we put dA over dt, the change in area compared to the change in time. And then on the right-hand side, we have to use the product rule because we're multiplying with variables. So we have L times dW over dt plus W times dL over dt. Just fill in these values, so it should be 12 times 2 plus 5 times negative 2. So 24 minus 10 is 14, and the units are square centimeters each second. Okay, so now, guys, what you should be doing, those of you watching this at home, is you should be going back and trying these like extra questions that I'm skipping. And then there's a more challenging one that I just want to give you a tip on how to approach. So we're going to look at 6. Water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5. How fast is the water level rising when the water is 6 feet deep? Okay, so let's write our equation. We know that volume of a cone, or people may not know this, but volume of a cone is 1/3 pi r squared h. And we don't know what the height of our water is at the time. Oh, I'm sorry. We do know that the height of our water at the time that we're interested in is 6. The height is changing, so we need to make sure we put the height as h, the variable. The radius, we don't know. We put r. But now, if I'm interested in how fast the water level is rising, I really want to know dH dt. I do know dV dt. A hint would be the units. They told me 9 cubic feet per minute. That's how much water is flowing in. That's the change in volume. Okay, if you were confused, this units would be a tip-off. All right, so now we're not really concerned with the radius, and we don't have any information directly given to us about the radius. So let's see if we can figure out a relationship between the radius and the height. Now, when I have like a cone, if I poured water in, it's not going to fill up like this, right? It's going to fill out the cone proportionately. And because of that, we can make a relationship, find a relationship between the height and the radius. So we can tell that in terms of the whole cone, the height is 10 feet and the radius is 5. As we fill up the cone proportionately, the radius and the height will have to stay in that relationship. So instead of r, we can really write 1/2 h. So before I do any calculus, I'm just going to write in, instead of r, like h over 2. Then I'm going to simplify this algebraically. I'm going to get pi over 12 times h cubed. Okay, then I'd like you guys to finish this. Take the derivative of both sides compared to time, plug in what you know, and make sure you get the units right. All right, good luck, guys.